Hello everyone. In this session, let me discuss the last concept of that is step function. So I have already told you in the previous sessions that I have combined first and second units together. Why? Because we cannot predict the questions that it will come from first lesson only or it will come from second lesson only. So we cannot extract and measure integration. So that is the reason I have combined two lessons together. So this will be the last concept. Step function. So this when I complete this session, that completes your second unit. Fine. Including first unit as well. Fine. So this is the last concept and the last theorem in the second unit. So this completes your first unit and second units together. However, in the next session, I'll start with the third unit. Let me start with the concept step function. So you're already familiar with this word step function. In your UG classes, you're just going to denote it as by writing certain values for one condition and another values for other condition, right? So in measurement integration, it is quite different. A step function f from a closed interval ab to r is said to be function. Suppose if a function f is defined from closed interval ab to r, then f is said to be step function if a closed interval AB can be partitioned. That is, whatever the interval I have, I can rewrite that interval as like C0 less than C1 less than C2 so on less than Cn. That will be the end value like B. So if I can partition a given closed interval AB in such a way, or I can say in such a way that f with restricted to Ci minus 1 and Ci is constant function. Let me repeat once again. Any function f defined from closed interval ab to r is said to be step function if a closed interval ab can be partitioned into n number of partitions, something like this, in such a way that f restricted to Ci minus 1 Ci. In the sense, when you're going to define measurability with respect to any two consecutive intervals, that should be constant function. Then we can say f is step function. So the minute when I say f is step function, these two conditions will be holds good. In the sense, I can divide a closed interval into n number of partition. Further, f with respect to or restricted to Ci minus 1 and Ci will be a constant function. Or as I can say f restricted to Ci also I can say is constant function. Clear? So this is what the meaning of step function is. Now coming to the last theorem of your second unit, we have to prove that f from closed interval ab to r is measurable. So you have already understand the concept of measurable function. Now we have to prove f from ab to r is measurable. This is the theorem. So in order to prove this theorem, let me take this is not exactly theorem, that it is just a concept. After this you have only one theorem. Fine. So I have already told you when I can say f from closed interval ab to r, I can divide this interval into n number of subinterval. I can partition, right? So I can write a closed interval ab as union of all the partitions. Fine. Whatever may be the case, either you can take like this. So you can note that I'm going to split each and every interval again. C0, C1, again I'm going to split it as C1. Again C1, C2, I can split it as C2. Whatever may be the case, if you continue this, I can write Cn minus 1 union with Cn minus 1 Cn union with Cn. So I'm going to write the given closed interval as union of all those partitions. Fine. And the minute when I said it is what we say step function, I can apply this concept, right? So f restricted to Ci is measurable for I, right? And moreover, I have already proved while proving the measurable function, we can say all constant functions are measurable and also all singleton sets are measurable. It is just a corollary of one of the theorem. You just go through the notes. I have already proved that all the constant functions and all singleton sets are measurable. I have given this as an example or corollary. You just check the notes. So all the constant function and singleton sets are measurable. So when all the constants are measurable and all the singleton sets is measurable, I can say f restricted to Ci is a constant function which is measurable. It is just a logic. So I have already proved that I have already divided the closed interval AB into n number of partition. We have to prove that CF restricted to CI is measurable for I, or it is a constant function with reference to one of the value I. So we have already proved that any constant function and singleton function or singleton set is a measurable, right? So it is expressed as union of all the singleton sets, right? Again it is measurable, and also a constant function is measurable. So by that I can say F restricted to Ci is a constant function which is measurable. Only 3 lines proof it is. Fine. And the last theorem is, suppose if F and G are two measurable function defined on a real number R. Let me write the statement here. Suppose a theorem is like this. Theorem: if F is a function defined from E to R, almost R is measurable, right? This is understood. R is measurable. And if B is a Borel set, hope so you remember the concepts of Borel sets, right? Borel set in R, then we have to prove F inverse of B is measurable. F inverse of B is measurable. While explaining the concept of Borel set, I have proved the theorem that every Borel set is measurable. But this theorem states that if B is Borel set in R, then we have to prove F inverse of B is also measurable. You just revise the concept of Borel set. What it says: a Borel set is a member of smallest sigma algebra generated by all the open sets, right? Smallest member of smallest, or else I can write this as member of smallest sigma algebra generated by all open intervals in R. So this is what the definition of Borel set says. It is just a members of smallest sigma algebra which is generated by all the open intervals in R. So suppose if B is a Borel set, we have to prove F inverse of B is also measurable. Now to prove this theorem, it is sufficient to prove these two lemma. So in the exam, if they asked you to prove this theorem, you have to prove these two theorems or lemma first. So first one is we have to prove that suppose if I have a set alpha which is such that A is subset of R, F inverse of A is measurable. In the sense, we are going to prove this for generalized case. For any set A, F inverse of A measurable, then we can generalize it for Borel set. And second thing is that we have to prove that this alpha contains all the open intervals in R. So remember, if they asked you to prove this statement, they will not give these two theorems. These two lemma you have to write. So in order to prove this lemma, first you have to consider this set, and we have to prove this set is measurable and alpha contains all the open intervals in R. And moreover, here remember alpha will be a sigma algebra, and you have to write the statement. I'll send you the notes, don't worry. So I have to prove that this alpha is measurable, where it is alpha is a sigma algebra. So you just remember the concept of sigma algebra. When do we say it is any set is sigma algebra? A set alpha is said to be sigma algebra when it is closed under countable union, right? Countable union. If it is closed under countable union, we can say set is a sigma algebra. Given that alpha is a sigma algebra, we have to prove this is measurable. Further, we have to prove alpha contains all the open intervals in R. Now let me prove this. Suppose if I have considered the given statement, that is alpha is a sigma algebra, right? Now let me consider an element A which belongs to the given set alpha. So given that alpha is a sigma algebra, and if you are going to consider any element A which is in alpha, that is in set alpha, by the definition of the set alpha, if any element belongs to this set, then F inverse of that element is measurable. Since A is belonging to real number, then F inverse of A is measurable. Here I have considered the set A which is in alpha, implies that F inverse of A is measurable. It is given in the assumption itself. So if F inverse of A is measurable, we have already proved that complement of measurable set is measurable, right? So complement of measurable set is measurable. So from that statement I can say F inverse of A complement is measurable. F inverse of A complement is measurable. Why? Because complement of measurable set is measurable. Now I can rewrite this as here. Now we have to show that we have to show that F inverse of A complement can be written as F inverse of A complement. So F inverse of A whole complement is equal to F inverse of A complement. We have to show that both are equal. Fine. Why? Because in a given assumption, what we have, alpha is a set which contains F inverse of A is measurable, and moreover it is a sigma algebra, right? So, and moreover we have to prove it contains all the open intervals in R. Now what I have assumed is, if I assume any element belongs to this set, as per the definition of we have defined set, F inverse of A is measurable. So we have already proved that complement of measurable set is measurable. By that I can say F inverse of A complement is also measurable. Now let me prove F inverse of A complement as F inverse of A complement. F inverse of A whole complement is different from F inverse of A complement, but we have to prove they are equal. So let me consider an element X which belongs to F inverse of A whole complement. So if X belongs to F inverse of A complement, I can write X does not belongs to F inverse of A. Right? Suppose if, let me consider this as an element, forget about function, let me consider this as an element. If X belongs to complement, X does not belongs to a original value, right? So in the same sense, like this, if X belongs to A, I can write X does not belongs to A complement, and vice versa. That is, if X belongs to A complement, then X does not belongs to A. So in the same sense, I can write if X belongs to F inverse of A complement, I can write X does not belongs to F inverse of A. Right? At the same time, I can say, let me shift this, then I can say F of X does not belongs to A. That implies F of X belongs to A complement. I am just shifting this. So F of X belongs to A complement implies that X belongs to F inverse of A complement. I can write like this. See here, I am going to shift the F again. I will get F inverse of A complement. Fine. So what I have assumed is X belongs to F inverse of A complement. What I have arrived is X belongs to F inverse of A complement. So from these two I can say F inverse of A whole complement is equal to F inverse of A complement. So if this is the case, it is measurable. Is measurable. Meaning is, I have taken an element A belongs to alpha. I am going to prove it is a sigma algebra. Now we have to prove alpha is a sigma algebra. Right? I'm just revising once again. You just listen to me. What I'm going to prove is, I have assumed the set. So I have to prove this is a sigma algebra. So as per the definition of sigma algebra, it should be, first condition is it should be closed under complementation. Right? And second condition, it should be closed under countable union. First, what I have assumed is, I have considered an element A in alpha. So as per the assumed set, if any element belongs to alpha, F inverse of A is measurable. So complement of measurable set is measurable. So that is why F inverse of A complement is also measurable. Now why I have assumed this condition is, if you show this is true, A complement will be there in alpha. See here, what I have taken is an element in first set. So by these two conditions, I can say F inverse of A complement is equal to F inverse of A complement. Meaning is, I can say A complement is also belongs to alpha. Clear? If this is true, if this condition is satisfies, I can say A complement belongs to alpha. That is, alpha is closed under complementation. Alpha is closed under complementation. First condition is proved. Second, we have to prove it is closed under countable union. Right? So let me consider, let AI be countable collection of sets. Countable collection of sets in alpha. Second condition I am going to prove. So if A is countable collection of sets, then F inverse of AI is measurable. Right? Why? Because AI is countable collection in set alpha. So set alpha, how the set alpha is defined? Set alpha is defined in such a way that F inverse of A is measurable. Since what I have assumed is, AI is collection of countable collection of sets in alpha. If set belongs to alpha, then F inverse of that set is measurable. By that I can say F inverse of AI is measurable for all I. Or else I can write this as I is equal to it will be satisfied for all the functions. So countable union of F inverse of AI is also measurable. Clear? Clear? Now we have to show that if it is closed under countable union, we have to show that this condition is true. That is, F inverse of AI will be equal to F inverse of union I is equal to 1 to infinity AI. We have proved the same condition for complementation. Right? So in the same sense, what we have proved for complement is F inverse of A complement will be equal to F inverse of A complement. So I have proved this condition for complementation. Now for the countable collection, if it is closed under countable collection, it has to satisfy this condition. That is, when you're going to take F outside, union inside, both the values will be same. So you have to show this just by taking an element in the same collection. I am going to use the same logic for the theorem also, for this theorem also. So let me prove here. Let me take an element X which belongs to first set, that is union I is equal to 1 to infinity F inverse of AI. So if this element belongs to this set, I can say X belongs to F inverse of AI for some I. For some I, in the sense it contains collection of I number of sets. So X belongs to collection in the sense I can say for one set, that is for some at least one I can say X belongs to F inverse of AI. Right? So I can write like this. Now if X belongs to F inverse of AI, I can say F of X, I'm going to shift this, F of X will be in AI. Right? So if F of X belongs to AI for some I, again I can express this as F of X belongs to union. It is just a reverse of the previous case. See here, if X belongs to union of all these functions, I can say at least for one I it will be belonging to one I, right? X will be belonging to at least one I. So I have shifted this. Since if F of X belongs to one AI, I can say it will be belongs to all the unions, right? So again I can shift this. See here, X belongs to F inverse, I am just shifting it, F inverse union I is equal to 1 to infinity AI. Now what I have assumed is X belongs to union I is equal to 1 to infinity F inverse of AI. What I have proved is X belongs to F inverse of union I. So by comparing these two, I am using the same logic that what I have used for the complementation. See, in the first case I have assumed that X belongs to first set. I have proved that X also belongs to second set. So by comparing these two, I can say this inequality holds good. In the same way, I have assumed that X belongs to first set. I have proved that X also belongs to second. By these two, I can say union I is equal to 1 to infinity F inverse of AI will be equal to F inverse of union I is equal to 1 to infinity AI. Meaning is it is closed under, that is I can say I is equal to 1 to infinity AI belongs to alpha. That is, it is closed under countable union. If you are going to consider any set AI, that is what we have considered the set is. AI is a countable collection of set. So union of all the countable collection of sets will be in alpha. As I already told you, if this condition satisfy, I can say it is closed under countable. I'll just write here, it is closed under alpha, right? Alpha is closed under countable union. Countable union. So first one is finished. So first we have proved that it is closed under complementation. Second we have proved that it is closed under countable union. Therefore I can say alpha is sigma algebra. Alpha is sigma algebra. First condition is we have proved. So what we have to prove is alpha contains F inverse of A is measurable set. We have to prove sigma is algebra. Alpha is sigma algebra. So I have proved that alpha is sigma algebra. Next what we have to prove is alpha contains all the open intervals in R. So let me prove alpha contains all the open intervals. Second one I am going to prove alpha contains all open intervals in R. Fine. Now for any element, let me consider for any two elements in R such that open interval AB, if you are going to consider any element in a real number, then F inverse of AB can be written as, from the definition of measurability of a function, I can write X belongs to E such that F of X belongs to AB. Right? You just revise the definitions of measurability function by the basic definition. I can write this. Right? Now further I can express this as intersection of, I am going to split this, F of X less than, meaning F of X belongs to AB, meaning is F of X will be in between A and B. So I can write this as F of X less than B intersection of X belongs to E, F of X greater than A. Something like when F of X belongs to AB, meaning is A less than F of X less than B. It is our basic concept. For each and every step I cannot repeat it. So after this step, if you want, you can add this. So by splitting these two, I can write f of x less than b and f of x greater than a. So I can write this set as intersection of these two sets. And by the characterization of measurable function, I have proved this is measurable and also this is measurable. You have to remember the statements of each and every theorem, then only you will understand the concept very well. The concept is very easy and just a logic behind that. There is a logic behind that, so you have to understand. So I have proved this as a measurable characterization of measurable function. I have proved this as measurable. Now I have expressed as intersection of two measurable set. Again, by the theorem, intersection of two measurable set is measurable. Therefore, whatever the RHS value is there, so you just need to listen my words. I am explaining reason for each and every statement. This is from the characterization of measurable function. I have proved this is measurable, this is measurable. Again, I have expressed this as intersection of two measurable function. I have already proved you that intersection of two measurable function is measurable. Thereby, I can say RHS is measurable. So if RHS is measurable, I can say LHS is also measurable. In the sense, what is the LHS I have? F inverse of AB is measurable. In the sense, F inverse of AB, in the sense, what is the alpha I have assumed? F inverse of A. A is here open interval AB. Meaning is an open interval AB belongs to alpha. Why? Because alpha contains set of all the elements such that are open sets such that F inverse of A is measurable. Since I have proved that F inverse of AB is measurable, I can say AB belongs to alpha. See here, for any element A belongs to alpha, then F inverse of A is measurable. Similarly, F inverse of AB is measurable in the sense AB will be in alpha. So meaning is alpha contains all the open interval AB. So I have proved the second statement. Alpha contains all the open intervals in AB. So I have already told you if it satisfies both the conditions, so I can say alpha is a Borel set. Alpha is Borel set. Further, if any Borel set B belongs to alpha, in the sense alpha, what I have assumed is alpha is a Borel set. Why? Because it is a smallest algebra, right? I have already proved that is alpha is a sigma algebra. Moreover, it is smallest sigma algebra. Why? Because it contains all the open intervals in alpha. Right? Whatever the open interval you are going to take in a real number, no matter how small it is, every open interval will be in alpha. Moreover, it is algebra. So as per the definition of Borel set is a member of smallest sigma algebra generated by open interval. So it is a open interval, again it is algebra, therefore I can say alpha is a Borel set. Now let me take the Borel set as B. If B belongs to alpha, say from the definition, if B belongs to alpha, I can say if A belongs to alpha, I can say F inverse of A is measurable. Similarly, if B belongs to alpha, I can say F inverse of B is measurable. And that is what we have to prove is. See here, B is a Borel set in R, then we have to prove F inverse of B is measurable. Just the logic we have to prove. First, alpha is a sigma algebra and it contains all the open intervals. That is the meaning of Borel set. If you are going to prove these two are true, it says that alpha will be a Borel set. So I have proved that it is closed under complementation. Again, I have proved that it is closed under countable union. Thereby, I can say alpha is a sigma algebra. Next, what I have proved is I have to prove it is the smallest sigma algebra. To prove that, I have to prove any open interval will be in the defined algebra alpha. So I have proved that. Thereby, I can say alpha is a Borel set. If you are going to consider any Borel set in alpha, I can say by the definition F inverse of B is also measurable, and that is what we have to prove. So this completes. Hope so it is clear. I am trying to explain each and every concept in detail, but I don't know how much you are going to understand. Please go through all the videos. Definitely hope so you will be understand. This completes the second lesson completely. First and second unit totally completed. So I cannot assure you that you will get 4 questions. No, I cannot say. Why? Because I don't know how the mind of question paper setter is. So anyhow, I completed first and second unit together. You have to read that together. You cannot partition the units. If you want, you can go through the question paper and you can plan for exam, and you can decide which unit you have to study. And anyhow, in the next session, I'll start with the third unit. If you want, you can refer the syllabus copy that I have already provided you. Hope so it is clear. Thank you. And notes will be forwarded in the group. Please copy the notes. At least you should have a notes with you. Then only you can face the exam. Hope you understand. Thank you. Continue in the next session.